Hi everybody, and thanks for joining this talk. This morning we've listened to very general topics, but right now we will go down into the specific and we're going to present a real-world application built using Akka streams. Don't worry if you don't know the basics, we'll go through them before reaching the advanced topics. First of all, who are we? I'm Gioia, I'm from Venice, so this is my hometown. I got my degree in computer engineering from University of Padua, and I spent some years working with web technologies like Python, Java, and Scala. Right now, I'm a software developer at Measurance, working on R&D, data analysis, and microservices.
Hello, my name is Simone, and before playing with Scala microservices at Measurance, I spent my time writing JavaScript code and JavaScript code.
So we both work at Measurance, but what does Measurance do? Measurance provides actionable insights for retailers with its analytics platform service. But what do we do in practice? We collect, analyze, and process data coming from sensors installed within existing and potential stores. Let's see together the agenda of this talk. We'll first start from the problem, which triggered us to use Akka streams. Then we'll dive into Akka Streams 101 in order to understand how we were able to achieve a stream-based solution, namely the collector service. And finally, we will draw the conclusion and discuss the key learnings of our experience. So in order to understand the problem, we have to first take a look at our data ingestion and processing pipeline, which is the very first implementation of our system. So how our system ingests the data coming from the sensors. This is an overview of our data ingestion and processing pipeline. Upstream, we have a bunch of sensors mounting Wi-Fi dongles and the 3G connection. Sensors capture Wi-Fi signals in the surrounding environment and send those data to more instances of the same Scala microservice, which is the one you are seeing in the middle, the collector service. The collector service analyzes and processes this data and finally sends the results to Amazon Kinesis. If you're wondering where this data will finish at the end, I can tell you that we have another service which purpose is to grab the data from Amazon Kinesis and store it to Cassandra. But this is beyond the scope of the talk. Perhaps we might hold another talk about this. So let's now concentrate on our data ingestion and processing pipeline. And now we will see how we implemented the collector service at the very beginning. Till 2 months ago, this was the architecture of the collector service. For each incoming TCP connection, Spray.io sent a message to the master actor existing in the system. Let's call it root actor. The root actor spawned a new worker actor and notified Spray that a new worker actor was ready to take care of the incoming TCP connection. At this point, Spray started sending chunks to the new worker actor, and messages started to flow from Spray to the actor's inbox. Once the actor had processed the message, he sent an event to another actor, the Kinesis client, which was devoted to perform the actual upload on Amazon Kinesis. Could you see any critical point in this architecture? If your answer is yes, then you may be wondering, is this really a reactive approach? Well, the actor model is one of the most important message patterns in reactive programming. So how could the actor model break the reactive foundations in our case? Let's check together the critical point of our architecture. The very first problem we may meet is message overload. Being specific, message chunks flow from Spray to the actor's inbox without any control, and this may lead to a memory overflow on the actor's side. But this may lead also to a very bad situation, the situation in which prolific sensors may steal all the resources available in the system, thus penalizing the less prolific ones. The main point is that there was no limit on the ingestion speed for data. The other main problem is given by connection outages. What did it happen when Kinesis was unavailable? Well, simply the upload of the events started failing until the service was up again. But this, of course, led us to lose all the events transmitted during the service downtime, and we cannot afford to lose any events since our business is built over data analytics. So we just seen the major problems in our architecture, and now we can see clearly why it wasn't reactive. In particular, if you remember the 4 fundamental properties of reactive programming and reactive systems, we can say that our system wasn't responsive since unbounded inputs made it impossible to treat clients fairly. And furthermore, some clients were possibly left behind others due to the lack of available resources. But our system wasn't even elastic, since memory wasn't in any way partitioned among the connected clients. And while unlikely, each client might have used as much memory as to store the others. So we really needed to implement 2 main important things to make our system reactive. The first thing is given by recovery mechanisms. This, of course, might have helped us avoiding huge data losses during connection outages, while the latter is back pressure on the network. Implementing back pressure on the network might have helped us in gaining control over the ingestion speed for data. So now let's go down deep into these 2 main important things. At that time, we had to think about possible recovery mechanisms and their implementation. So here the focus is on the stage in which the service has to send some events to Kinesis. So what should have we implemented when Kinesis was unavailable? Well, in order not to lose data when Kinesis was unavailable, we might have implemented a buffering system in which unsuccessful messages were stored and retained for later use. In this case, this buffer might also have been periodically emptied by writing the data on disk if it fit. And well, I can tell you that at the end, this was the solution we've adopted to achieve robustness when dealing with Kinesis. But what about upload failures? Well, we might have retransmitted the unsuccessful messages until they were finally received. But could you see any pitfall in this implementation? Here the problem is that the network might be more congested than ever, sending tons of messages while we don't know if we will succeed makes simply the message overload a bigger problem. So what we really needed was back pressure on the network. But what can we achieve by implementing back pressure on the network and keeping the ingestion speed under control? Well, think about the situation in which sensors are sending data at a rate that's not sustainable for the downstream components of the service. In this case, thanks to back pressure, the sending rate will progressively slow down, thus giving a breath to the downstream computation unit. At the same time, sensors are constrained to less data, and we risk to lose some information coming from the sensors. However, this can be controlled by instructing the sensors to retain the surplus information in their own built-in buffer. But there's another bad situation that could happen. Think about the situation in which sensors are so prolific and the downstream computational unit are so overloaded that back pressure completely prevents sensors from sending data. If this situation persists for a certain amount of time, then sensors will be disconnected from the current busy service and will be reconnected to the less busy one by passing through a load balancer. So achieving back pressure on the network for gaining control over the digestion speed for data is the driving motivation that allowed us to use Akka streams. Furthermore, there are some bonuses. We found that reading a flow implemented as a stream is far more readable than reading a flow implemented as with the actor model and sending actor messages around. And furthermore, the event types in Akka streams are checked at compile time, while in the actor case, they are not. Now Simone will talk about Akka Streams 101 and how we use it to improve the collector service.
Thank you. So I imagine you can understand what a stream is. So you have data that comes from one point and goes to another point. And probably in the middle there are some transformations. So with Akka Stream, you have these basic pieces that you can use to create your stream. So you have the source, and you can imagine the data is coming from there. Then you have the flow pieces where you do your transformations, and then the sink when you can close the loop or do something else. This is an example of code using Akka Stream. There is a sample source, a sample flow, and a sample sink. You can easily guess what these pieces do. When you put them together, you obtain an instance of a runnable graph that is actually the only object that can be run with the Akka Stream. So you call the run method on your runnable graph, and your stream will be materialized and will start processing data. Each of these pieces, from the source to the runnable graph, are immutable. So they just describe what your stream is going to do. But the real doing is only started when you call run. And so you can reuse the same pieces to compose different streams, or you can run your runnable graph multiple times, and these lives will be separated one from the other. The flow class, the flow companion object, has quite a few factory methods that you can use to create blocks to transform your data. So you have a lot of methods that are similar, if not the same, as the collection, the Scala collection. So you have map, you have take, you have fold, whatever. You don't have the flat map method to avoid confusion, because you can't run for comprehension on a flow. But you have a similar method that's called map concat that does the same thing. So if you need flat map on your flow, just use map concat. And then it has some extras that are clearly oriented to the stream. So you have the buffer, you have something for rate control, you have map async to run asynchronous transformations. This is how the stream actually runs. So we have the data that goes from the source to the sink. But actually, before any one of these pieces can send something down the stream using the push call, it has to receive a pull call from the pieces that are downstream. This is the foundation of the back pressure, because this way a downstream piece will never be overloaded, because it will only receive the data it is ready to process. Now that we have seen the basis, we'll go through our implementation, sort of. And so let's start from the web server. If you ever used Spray.io, you will notice that there are quite a few similarities. So the route is right in the same way. The API is quite identical. And the nice thing of this route that is written with the Akka HTTP is that the data bytes object is a source object. So you can apply back pressure on it. And if you apply back pressure on it, it will apply back pressure on the network. And that was our main goal for this implementation. That processing call creates a flow instance that is our processing, so we'll see it later. And then we use a sync ignore. In this case, this sync does nothing, just gets the data and discards it. We chose this approach instead of putting some logic in the sync because flow are much easier to be tested. We'll see a case later. So we put things together as we've seen on quite as the same way we've seen on the first slides, and we start consume data from the network. So this is the beginning of our flow. The chunk buffer. The chunk buffer is an instance that receives the chunks from the network, and but our protocol is line-based, so we need to separate the data that is coming in into line strings, in strings. So we need to change this chunk. Each chunk may contain more lines or may contain alpha line. So we need something to process this thing. And another thing to be noted is that this piece, this flow, will emit not the same number of events that it receives. So there is also this particularity. The chunk buffer is implemented using one of the main utilities of Akka stream, in this case the framing delimiter. We just specify our separator, and then apply some transformation to remove the separator and make it a string, and we are done with it. Next step is to transform these strings into objects that represent our event, but this part is not interesting, so we skip. And then we have one of the other goals of this implementation, that is the persistent buffer. So we want a buffer so that we can ingest a few data from the network, even if we can't consume them at once. But we want this buffer to be persistent so that in case of failure, we don't lose this data, but we can go back later and recover them. There is no utility in Akka Stream to do this ready-made, so we implemented our own stage. And we're going to see how you implement a stage with Akka Stream. So the first thing you have to do is to specify the shape of your stage and extend this graph stage. Actually, there are other classes that you can extend to implement a stage, but the graph stage is the basic one. So let's see this one. In this case, we specify a flow shape because we want the data to come in and then data to go out. Then we specify our ports, we put things together, and the initialization of our class is made. Next, we want to implement the logic of this stage. You might see that this part is wrapped in a create logic class call. This is because, as I said, the stage itself is immutable. But when the stream is run, this call is made, and you have to return to it a graph stage logic instance. That's actually what is going to run your logic. For this reason, the state of the stage must be placed here, because if you place it before in the main class, you will share the same state across all your instances, and that's not what you want. A particularity of the stages is that, like the actors, each stage is always run on a single thread, meaning that you'll never have two pieces of the same stage running at once. For this reason, if you need to run something that after a future is resolved, you can't use directly the callback, because the callback of the future will be run on a different thread and you don't have any control on that. But there is this getAsync callback call that can be used to wrap your callback so that when it is executed, it will be run on the thread of your stage. So this is nice. You just wrap your code and pass to the future. This getConcurrent queue is a future, the invoke function. Next, to implement the flow of the data, you have to implement an handler per each of your ports. So in this case, an in handler for the input port and the out handler for the output port. You'd have to override the, for example, in the input port case, the onPush method. This one is called when the upstream piece is ready to give you something. At that point, you have to grab that something, because it's not part of the call. You have to grab it, and then you can ask for more using the pull call. The pull call will call the onPull method on the previous stage, so not on this one. And that stage will be maybe sending something to you using the push call. To be noticed is that the sequence of things that have to be done must be done in a certain way. Meaning, for example, you can't push twice without getting an onPull in the middle. This is, again, to force the contract of the stages that make back pressure part of the Akka stream implementation. Again, like actors, you have hooks for start up and tear down. So if you need to prepare something before the stream is run, or if you need to release resources after it, you can do with these methods. Next, now that our data is safe, we are ready to send it to Kinesis. And we use this Kinesis publisher. To implement it, we use the map async that we've seen on one of the previous slides. This map async will map an event that is coming from upstream to a future. I mean, you have to give it a function that maps the event to a future. And in return, the map async will wait for that future to be resolved and will emit the resolution of the future downstream. So here we return a future of publish completed, but the next piece will receive the publish completed. If the future fails, the whole stage fails, and by default, all the stream will come down. Next, the publisher. The publisher is actually an actor, and we talk to it using the ask pattern. So we send to it this publish request. This actor will try and retry to send that event to Kinesis until it succeeds, or until the timeout of the ask pattern is failed. To avoid failing your stage in case of timeout, you might attach a recover to this future, or you may use a trick, meaning that your actor, upon receiving the publish call, will create a promise and return the future of that promise immediately. So the ask pattern will be fulfilled, and you'll get a future of a future that you can flatten and then emit downstream. That was the core of the implementation. We also have used some of these also two calls in the middle of this stream, not necessarily at the end. And these also two permit to attach side effect to your stream. So you simply specify, in this case, a sync. And this sync will receive all the elements that are passing through this stream without being able to modify it. So we, for example, use it to update our metrics that are then sent to Grafana, and we have the nice visualizations and stuff. Another thing to be known before starting writing code with Akka stream is that while I said that a stage is always run on a single thread, actually that's true for the whole stream. So by default, when you run your stream, there will always be at most one stage running at any time, unless you use that async call. In our case, that's not necessary, because we have a lot of streams that are running concurrently, so we already have parallelism in our application. But if you have a few streams or just one in your application, you might need this so that you can spread the load across different threads. Obviously, running on a single thread have an advantage from the point of view of communication, because you don't have to synchronize anything for the various stages to talk with each other, and so you get faster code. But on the other hand, if you have just one stream, you won't be able to use all the cores of your machine. When you run a stream, you can also extract a value from each of the stages that are a part of the stream. This value that you extract is not part of the stream itself, but is something else that the stage wants to give you right away. So, for example, the sync ignore will give you a future of done. That is simply a future that is resolved once the stream is completed. A good example of materialized values is the test kit of Akka stream. So the test kit exposes two classes, the test source and the test sink. And these classes will materialize with the publisher and the subscriber. So the test source will give you a publisher that can be used to publish events inside the stream. So you get control from the outside. While the subscriber can be used to check that what is received is what you expect. So this way, using both the test source and the test sink, you can test your flows as if they are functions. Yeah, it's just a little bit different, the code, but you can see the same kind of test you can run on a function. This is why I said that running tests on a flow is much easier than testing a source or a sink. What's this? Oh. I said that when an exception is thrown, or maybe I didn't say it. Anyway, if you throw an exception during a stage, that stage will fail, and by default, the whole stream will be teared down, because the failure is spread across the whole stream. You can avoid that using a supervisor that, again, is similar to what you can do with Akka actors. And this supervisor can be attached to a piece of the stream or to the whole stream. So you choose which part of the flow this supervisor will control. And it will receive the exceptions that are thrown by the various stages. At that point, based on the exception that you receive, you can choose to resume the stream, meaning that you will drop the event that caused the error, and you will keep going. Or you can reset. That mean that you will still drop the element, but you will also reset the stage. So the create logic that we have seen before will be recalled, and the state of the stage will be back to square zero. Or you can stop, meaning that the stream will fail, the stage will fail, and the failure will be spread across the stream. Last, up until now, we've seen just a linear stream. So we had the source, the flow, and the sink, and with that you can just create a linear stream. But actually, Akka stream supports other kinds of shapes. So, for example, it has a fan out. So let me make an example. There is the broadcast method that is built in with Akka stream. So it will receive from upstream something, and it will emit the same something to two different stages. And you can imagine you can have other kind of shapes. If you put these together, you can create complex graphs with feedback loop and whatsoever you need. But this is outside the scope of this talk, and I'm not going to talk about it now. So with this, we finally got reactive. So our application is able to withstand the many sensors we have across the world. And I think Gioia has something else to say before saying goodbye. Thank you.
So we finally were able to get reactive, but what did we learn from this experience? Let's do a brief recap and let's check together the key learnings. We started with a system which in upstream we had a bunch of sensors that send information through a collector service, and finally this information was uploaded on Amazon Kinesis. The very first implementation of this system was subject to memory leaks and data losses. But we've also seen that thanks to Akka streams, we've been able to implement back pressure on the network, and in particular thanks to its push-pull mechanism and thanks to custom stages. We've also seen that thanks to persistent buffer, we were able to implement a pretty robust recovery system. So here we see the key learning of our experience. Despite we used the actor model at the very first beginning to implement the collector service, we didn't achieve a reactive system. So actors aren't sufficient to be reactive. Furthermore, Akka Streams API is rich. In what sense? Akka Streams offers a lot of utilities that you can use and adapt for your custom purposes. Let's make an example. At the very beginning, we started developing a custom stage in order to attach a side effect at the stream ending. But we finally realized that there's a built-in tool in Akka Streams that performs exactly the same thing. And finally, achieving back pressure with Akka Streams is pretty straightforward, since it is a building block. It is a building block and it is implemented by design. So that's how with Akka Streams we've saved a lot of sleeping hours that we've lost in preparing this talk. So thank you. Any questions?
Hi, thank you for the talk. It's interesting, very interesting. So I have two questions actually. The first one is related to did you gain some advantages on processing? Did you gain some advantage on processing using Akka Stream with respect to Akka, apart the back pressure and other stuff? Another question is, can you tell more about the materialization process, because you talk about the async, and when you add an async on your stage, you're actually creating another actor, and so we'll go multi-threading. So there are some advantages and pro and cons on using async with or not async, especially if you have streams which are, so we have some nodes which are slow and other nodes which are faster than others.
So about the first question, there were many advantages. The first one was readability. So you can see. This is more or less what our code looks like. And this is a big plus, because before you had just a message that was going to an actor, and then you had to follow that actor to see what was going to happen to that message, and so on and so forth. So this is one of the big advantages. Second advantage is the typing at compile time. So we know we are forced by the compiler to emit the right kind of events from each of these stages, while with actor you can send anything, and so you might get unexpected errors when you run your code. Other than that, no, meaning that a lot of part of the code are actually the same. Like the Kinesis publisher is actually the same implementation. Well, we added the retry mechanism, but that's not strictly related to Akka stream. It was just part of the refactoring of the whole service. As for the second question, I forgot. Okay, again, that depends on what you do here, meaning that by default, when you run your stream, you probably create just one actor. And that actor is running all the stages. So that's light. Yeah, exactly. By default, it fuses everything. If you don't want the fusion, you have to use these async calls. And at that point, each of these async will create a boundary in your stream. So in this example, there are 2 boundaries. So this stream will run on 3 actors, because there will be the first actor that will run the source and the first do something. The second actor will run the do something, and the third will run just the sync. But anyway, as I said, if you have a lot of streams, like we do, you don't need this, because you already have a lot of streams. You will have so 1 actor per stream. Anyway, I get that actors are lightweight, or at least they are publicized like that, so I trust they are. And yeah, I don't think we saw any change in the load, even if we added a lot of logic to the service. So I say I'm positive.
Can I make a two-way stream? Like when the sink is a source and the source is a sink, so the data is synchronized between 2 parts using the flow, something like this.
Okay, so there is actually a shape that is called BD flow that I didn't show, that is used by the Akka HTTP implementation to implement the protocol. So in this case, the BD flow has 2 input ports and 2 output ports, and is actually used to run 2 streams in the same stage concurrently. So I think this is what you asked for. So you can do that. Also, we tried to use different shapes to do the retrying of the failed messages to Kinesis. So there was a stream that was like send the message, and in case of error come back. That actually has a lot of complexity in it, because you can create easily a deadlock when the pull calls do not match, meaning you have the pull request that go to the real source, and the pull requests that go to the retry mechanisms. And if these are not balanced, and if you don't put a buffer in the middle, you risk to block all the pull to the real source with pulls to the retry, because again there is also an inbox, like an inbox between the stages. By default, I think is 1 or 2, and you can easily feel that. We actually succeeded in using this kind of mechanism, but in that case we didn't have a stream of events that was flowing concurrently, but the stream just had to handle one single event. So the event got in case of error it went back, and that was kind of easy and had no problems. Honest?
Hi. First of all, sorry if you already mentioned it. Maybe I missed it. While I was reading about reactive streams a long time ago, you hear me? Okay. I read that it's regarding the push-pull mechanism. I read it's not strictly pull or push in order not to overflow the subscriber, or if subscriber is fast, then it would waste resources. But instead, it's what they call effectively push. So the subscriber asks for n pieces of data, and publisher is free to push until this is reached. This limit is reached. Is this how Akka streams work, or is it different? So basically, pull, but not for just one piece of data, but for example, pull for 1,000, pull for 2,000.
Now, in this case, there is actually a one-on-one correlation between the pull and the push call. It was a design decisions by the guys, the great guys at Akka. So no, you can't push as long as there is room. You just push one when you get a pull. If you need to push a lot of data at once, you can place a buffer. There is a flow.buffer. It's a factory. You specify how big this buffer is. You put that in front of downstream to your stage, and then that buffer will call pull until it's full. At that point, you have to choose what to do, and you can say, okay, when the buffer is full, back pressure, or when the buffer is full, drop the last element, drop the first element, whatever. Anyone else? Okay then. Thank you.